This DeBacco University video is going to go over electrons, relation to energy levels, and you may remember, or this might look familiar, as like the Bohr model or planetary model to develop hopefully a deeper understanding of this concept. Now those electrons and energy levels, also called electron shells, are the specific regions around the atom's nucleus where electrons are likely to be found. They act like a building where each level can hold a certain number of electrons and has a specific energy. So while we're going to think about them as if you're in an elevator, like different distinctive floors where you can't be in between them, realize that electron cloud model is kind of the more accurate and real world kind of how things might interact and act in an atom. But we're going to kind of, just for simplicity, think of them as distinctive energy levels. So remember, electrons, they're negatively charged particles, occupy quantized energy levels around the positively charged nucleus. The lower the energy level, or the closer to the nucleus, will be filled first, the closest one being considered the ground state. And the higher energy levels are further out and have more energy. Think of that as if you're walking upstairs, you've got your ground state. It takes energy to work your way up those distinctive steps. In this case, we're using those steps metaphor here to think about those different energy levels. Now, how many electrons can each level hold? Well, we've got energy shell 1, 2, 3, and 4 for the most part. Maximum, that first energy can only hold 2. If you want to think about this, think of the periodic table. You've got hydrogen and helium at the top first period there, and there's only 2. They can only hold 2 electrons. Energy level 2 can hold 8, 3 can hold 18, and 4 can hold 32. This does correlate with the periodic table. And note that these are maximum number of energies that they can hold. They can hold less than this, and we would always build from that ground state and work our way up. Atoms don't always fill all energy levels completely, and when we work with notation, so we're working within this unit, 1s, 2s, 2p, 3s, 3p, 3d, these might sound familiar as well. And we see again a visual representation here of these different energy levels and what the maximum number of electrons that they can each hold. Now, jumping electrons, so electrons can move between these. Electrons can jump between energy levels by absorbing or basically releasing energy. When they absorb energy, they're moving to a higher energy level through an excited state. When they're releasing energy, they're falling back down to that ground state, often emitting light when they do. And depending how far they fall, that can determine the energy released, and that can also relate to the wavelength released, which directly correlates with the color that we perceive them releasing as they're dropping down to that lower energy state. Now again, using the Bohr's model here kind of makes it a little easier to kind of conceptualize. Electrons are not randomly scattered, but in specific circular orbits around the nucleus. We simply label them 1, 2, and 3, and where n is the principal quantum number, which is directly related to the energy level. And the closer the orbit is to the nucleus, the lower the energy is. Now again, for Bohr's model, electrons exist in these fixed orbits. We're going to think about them here. Even though they do exist in that cloud, this makes this concept a little bit easier to understand. Each spectral line in the visible region is produced when electrons falls from a given energy level to the ground state. We can see here as it falls greater, we see more of that violet light. As we see a less of a jump there, or less of a difference, we're seeing more of that red wavelength there. Now, units do matter, so nanometers measures the wavelength of light involved in electron transitions. It's inversely related to energy. The shorter the wavelength, the higher the energy level. You want to be comfortable or at least familiar with converting from meters to nanometers, because sometimes you might be given one unit and need to convert to the other. So here's an example of 322 nanometers being converted to meters, where 1 meter is the same as 10 to the 9th nanometers. We see our nanometers cancel out. 322 times 1 divided by this 10 to the 9th would get you a wavelength of 3.22 times 10 to the negative 7th meters. And this might be needed when we start adding this concept as part of different equations.